Hello students, I'm your lecturer Mr. Fun Man, and today we'll be going through this topic on the atmosphere. The atmosphere. As you all know, the atmosphere is a layer of gas that surrounds the planet. So this layer of gas is held down by the Earth's gravity, and without gravity, the gases will be expelled into space. But unlike the atmosphere of the other planets, the Earth's atmosphere is very unique because it has properties that allow the Earth to be a life-bearing planet. But before we go into such details, let's look into the composition of the Earth's atmosphere. Now, the composition of the Earth's atmosphere is found out with great precision and accuracy by a scientist named Dr. Henry Cavendish in 1785. Over the centuries, the atmospheric composition has changed slightly than what was discovered by Henry Cavendish. Today, we know that the atmosphere is composed of the following gases in their respective percentage volumes. Majority of the atmosphere consists of nitrogen gas, 78 to 79%. The other bulk of it comes from oxygen, that's worth from 20 to 21%. And of course, we remain 1% for the other gases, like the noble gases, your argon, neon, helium, hydrogen, and xenon. And you'll notice that as the lower the density of the gases, you have a lower percentage because they are in a way lighter, so they will be higher in the atmosphere. The other variable gases are your water vapor, CO2, methane, the nitrous oxide, NO2, the ozone, and the chlorofluorocarbon, the CFC, which exists in trace amount. And the four of them are called the bad boys: the carbon dioxide, the ozone, the nitrous oxide, and CFC for certain reasons. Which of these gases can you figure out are greenhouse gas? Which of these gases traps heat? We'll find out later. Now try to recall, nitrogen gas, is it detectable by FDRO spectroscopy instrument? This is the very stable diatomic molecular gas with NN triple bond with a super high activation energy, and naturally you need to have lightning to be able to react this N2 with other gases to form like nitrous oxide or nitric oxide. Now we know that N2 is not detected by FDRO because it is homonuclear, and when the bond expands and stretches like a spring, there's no change in the dipole of the molecule. Next, about 20 to 21% of the air, oxygen, it makes up a significant amount of what we breathe in, and that's why we are able to stay alive. And this is what sustains human being. Now, again, this is similar to N2, but it has got a double bond, O double bond, a homonuclear diatomic molecule. It is also not detected by FDR for the very same reason. Now, oxygen is paramagnetic, and it gets weakly repelled by a magnet. If you recall your junior years in inorganic chemistry, you can use the MO diagram to figure out, to explain why is it so. Now we know that right now in the Earth that we live in, oxygen makes up about 20 to 21% by volume of the atmosphere. Now before the atmosphere was filled with oxygen during the Proterozoic period, life is restricted to a single cell organism, and only after the oxygenation of the atmosphere do scientists see the evidence of complex multicellular metazoans in the fossil records. Right. Now this is the MO diagram, the molecular orbital diagram of oxygen here to illustrate the paramagnetism of O2. So using the rules of filling up electrons, you know that the valence electrons of the O2 molecule has unpaired electrons singly filled to the pi star orbital of the 2p. And because you have electrons that spins, it is paramagnetic, and they do not cancel each other out. Next, we come to hydrogen gas. Hydrogen gas has one of the lowest density of all the gases. In a way, you can say it's the most ideal gas if you consider it is ideal. It's found in trace amount in the atmosphere, and this is discovered by the same scientists who studied the atmospheric composition. Who was that? Dr. Henry Cavendish. In between the years 1766 to 1781, Now, being lightest of all gases, and when I say lightest, I mean lowest density, it is not usually found at ground level. So it will rise up to the highest layer of the atmosphere due to its buoyancy. The noble gases comprises of the helium, neon, argon, krypton, and xenon, and the noble gases is in this group of chemically inert elements, with argon being the most abundant by volume at the atmosphere, taking up to about 0.93% of the atmospheric volume. Now, these gases are so inert that they naturally exist as a monoatomic particles. Only the heavier noble gases are reactive enough to react with fluorine, the most reactive element. And you can imagine that only starting with argon, it can react with like fluorine or even oxygen, going down the group here to form a compound. And that's because you have a very electronegative elements like fluorine and oxygen to stabilize the positive oxidation state of the noble gases. And because there's no bond inside the noble gas, so you can't detect it by FTIR. Right. Next, the other variable gases, your CO2, methane, nitrous oxide, and CFCs. Now, these gases are usually considered air pollutants nowadays. And CO2, CH4, methane, they are the greenhouse gases. The nitrous oxide causes acid rain, and the CFCs damages the ozone layer by the radical reactions. And as the saying goes, the dosage determines the poison, right? Too much of these bad boys, these bad gases, will bring around the detrimental effects on our atmosphere. So we will discuss some of these in the subsequent chapters. Now, if you can remember, what are some of the common names of the other oxides of nitrogen? Do you know the formula? N2O, what? Dinitrogen monoxide. What is that? Right. You have got NO, that's what? Nitric oxide, nitrogen monoxide. NO2, nitrogen dioxide, the brown gas, right? And are you able to write the chemical equation to explain the acidity of N2O? Hope you know. So that sums up this opening chapter. Citations for you.